Good morning, everyone. I first begin by thanking the organizers for giving me an opportunity to speak in this conference, which is dedicated to the memory of Professor Rajashekaran. And Professor Rajashekaran, as I had a fortunate time to have interact with him. I had an overlap of 5 years with him. And he, as Murthy said, he had very wide interest. He used to keep on asking me about the recent developments in lattice QCD. I discussed some of it. And it is a pleasure to share with you some of the results from lattice QCD side in this conference, which is dedicated to his memory. So I will be talking about specific topic in finite temperature and density QCD. And then there is another talk by Tanishq, who will talk about hadron spectroscopy, exotic hadrons in the heavy quark sector. And also there are posters by Bhavani and Navdeep. You must have already seen them. So by discussing about the recent results in lattice QCD, and we pay a tribute to Professor Rajashekaran. So my topic today will be understanding the role of chiral symmetry in the QCD phase diagram. And why is it important? Because it is believed that there was a QCD phase transition which happened at very early on in the evolution of the universe, about 10 to the power minus 6 seconds after the Big Bang. And this QCD phase transition is very important because it accounts for almost overwhelmingly large amount of the visible matter that exists in the universe, more than 99%. So all the substance that is made up of the visible matter is made up of hydrogen, helium. All of these owes their existence to the QCD phase diagram. So I took a plot from the recent website from CERN about the QCD phase diagram. So here on the y-axis is the temperature and the x-axis is the baryonic density normalized by the D0, which is the nuclear saturation density. And the important point I would like to convey here is most of the phase diagram is unknown. So all these yellow bands and everything, these are all unknown. There is no first principles calculation of the phase diagram, not yet known. Studies from model quantum field theories which have same symmetries as QCD tell us that there may be a first order phase transition at high baryon densities and low temperatures. And what we know definitely from lattice studies is this region of the phase diagram at high temperatures and relatively smaller baryon densities. Smaller meaning it's much smaller than the nuclear saturation density. So it's nuclear saturation density, we are somewhere here, and saturation density plays a role in this region. And the primordial universe, the trajectory that happened during the evolution of the universe must have gone through this region. And we know definitely from lattice studies that there is a phase transition from a phase of color neutral hadrons to a phase where there are quark and gluon-like quasi-particles, or the color degrees of freedom are liberated. And this phase transition happens it is not a true phase transition, but it is a crossover. And we know the crossover temperature very well. And there are two different mechanisms that give rise to this whole phase diagram here. One is called the chiral symmetry breaking, whose experimental signature is that we see pions which are much lighter than all other baryons or hadrons present in this world. And the second is deconfinement. So color degrees of freedom are liberated. And these two mechanisms drive the entire phase diagram here. And the most challenging part of it is to understand the mechanism of chiral symmetry breaking and confinement, which is still an unsolved problem. So I will talk today about the chiral symmetry in QCD and not about the aspects of confinement. So in QCD, even with physical quark masses, the light quark masses are much smaller than the intrinsic scale of QCD, which is the lambda QCD. So even when we talk about the physical QCD as 2+1 flavor, it respects and unitary symmetry U to left cross U to right to a very good extent. And this is what we call as the two-flavor chiral symmetry. Now, one can write these unitary matrices in terms of special unitary matrices. And when we talk about chiral symmetry breaking versus restoration, so the chiral symmetry breaking means that the SU2A part is broken, which leads to pseudo-Goldstone modes, which are the pions. And this is the non-singlet part of the chiral symmetry. So when we know the phase transition happens, which is a crossover. I should not tell a phase transition, but it is a smooth crossover. And we know the temperature at which it happens to a very unprecedented accuracy. So we know it up to 1% precision. And I was involved in this work as a postdoc, and then there were some other groups also which confirmed this value. But when we talk about this temperature, this is the temperature at which the non-singlet part of chiral symmetry is restored, beyond which it is restored. Now, the question that we would like to ask is what happens to the anomalous UA part of this chiral symmetry? When is it effectively restored? Now, why is this question interesting? Because though it is a subgroup of the entire chiral symmetry group, however, the non-singlet part is anomalous because of the chiral anomaly. It is always broken due to quantum effects. So, and from this relation, we can see that this UA1 part is related to the index of the gauge fields, and hence its breaking, the origin of its breaking is topological. And even though it is not a symmetry, exact symmetry, but there has been model quantum field theory studies which share the same symmetries as a two-flavor QCD, and people can tune the amount of UA1 breaking in these models, and it has been shown that the magnitude of this UA1 breaking term in all of these models actually determine what will be the nature of the phase transition, whether it is first order or second order, when in the chiral limit of QCD. Of course, when we switch on the masses, the exact phase transitions become a crossover, but the universality behavior always stays there. The mass dependent corrections always overwhelm that part. But the important point is UA1 part of the chiral symmetry, even though it is anomalous, it affects the nature of phase transition in two-flavor QCD, QCD with two light flavors. And of course, if we can find an answer to this question of how UA1 restoration happens effectively, it will never be exactly restored because it is always broken due to quantum effects. I will discuss what is the meaning of an effective restoration in the next slides. But if we understand the dynamics of these thermodynamics of this UA1 restoration, then we can also understand the topological origin of chiral symmetry breaking, because ultimately we want to understand why these mechanisms are happening from very fundamental perspective. So, as I already mentioned in the last slide, since UA1 is not a symmetry of the partition function, so there is no order parameter to study this. So, we usually study it from the properties of hadrons. So, whenever hadrons with specific quantum numbers, so what happens here is we look at these two hadrons. This is flavor singlet, flavor. So this is a Dirac scalar, but it has a flavor index, and it belongs to the scalar isotriplet, and this is pion, which is also a flavor isotriplet, as well as it has a gamma 5 index. Whenever these two hadrons or hadronic correlation functions become degenerate, then we actually can tell that UA1 is effectively restored. So this is one of the ways one can study these problems. So one looks at integrated correlation functions of hadrons carrying these quantum numbers, and one has usually people look at the 2-point correlation function of these hadrons, and then whenever these correlation functions become exactly the same, this is the temperature at which the UA1 is effectively restored, and this is how we characterize this. Now, this is a very hard problem because This is a non-perturbative problem, so we have to do it through a non-perturbative regulator. We use lattice QCD, and whenever we do study these problems on lattice QCD, we have to discretize our action. So we have to choose some discretization for the Dirac operator, and most of the known discretization of the Dirac operator preserves only a remnant part of the continuum chiral symmetries, all except one, whichever is computationally more accessible till now. And then that's why it is important to see how well all of the chiral symmetries are actually preserved on the lattice, even after doing all this discretization. So for that, we have Ward identities. So one can study these correlation functions. So this chi is the integrated correlation function of the pion, chi pi, and the chi delta is for the delta meson, which was the scalar isotriplet. And by Ward identity, this, when the chiral symmetry is restored, then this difference between pi minus chi delta is related to the disconnected part of the chiral susceptibility. So here we choose a particular discretization of fermions, which is called the highly improved staggered quarks, and one calculates these two quantities on the left side and the right side. So the open symbols are actually this quantity in the right side, and this should be exactly same when we are in the chiral symmetry restored phase. And what we see is when chiral symmetry is restored, these all merge on top of each other, so we cannot distinguish these points. So the Ward identities are satisfied even with this kind of discretization, and we are varying these numbers. When you go to larger n tau, means we are going closer and closer to the continuum limit. So the agreement becomes much more better when we are near the continuum limit, or final lattices. Now we also studied the relation between the topology and the UA1 breaking. So if you look at the Ward identities, then this chi disconnected part of the chiral susceptibility is related to the topological susceptibility, which measures the fluctuation of the topological charge in QCD. And by comparing, we can calculate these two quantities independently and see how well it matches. So that is what we did here in this plot. So this topological susceptibility is given by the green band. The band represents the error when we take the continuum extrapolation. And this red is the disconnected part of the chiral susceptibility multiplied by the light quark mass squared, and all of them are taken to be the 1/4 power. This is studied as a function of temperatures, and these temperatures, you can note that is in the chiral symmetry restored phase, and we see that these agree very well with each other. And one can also characterize the temperature dependence at very high temperatures, beyond 2 times the chiral transition temperature. So beyond 350 MeV, the temperature dependence can be given by the dilute instantaneous prediction. So by this, we can now see that this UA1 breaking has a topological connection. Now one can also study these correlation functions in terms of the eigenvalues of the Dirac operator. So if one calculates this in the infinite volume limit, one can relate this correlation difference in the correlation function of the pion and delta to the eigenvalue density divided by this quantity, where lambda are the eigenvalues of the Dirac operator. Now we have to do these calculations at finite temperature. In 0 temperature, there are various relations relating these eigenvalue densities through chiral perturbation theory, but at finite temperature, very little is known. There has been studies which began 10 years before, or more, little bit more than that, and usually all the calculation goes by assuming that this eigenvalue density, which is a function of the eigenvalue as well as the light quark mass, it is an analytic function in lambda and m square. And then Ward identities, chiral Ward identities are used to derive relations between these correlation functions. And then by studying all of these correlation Ward identities, people have found out that if these assumptions are valid, then if one sees that the eigenvalue density goes as a power of lambda cubed, then this is a necessary condition for the breaking of U1 to be invisible in correlation functions of the scalar and isoscalar up to 6-point correlation functions. Now the question we want to ask is this eigenvalue spectrum always a polynomial in lambda, which goes into all of these analytic calculations. Yeah. Lambda is the eigenvalue of the QCD Dirac operator. So, in general, one can write the eigenvalue density as some constant part, which gives you the intercept here, which is related to the chiral condensate through the Banks-Kasher relation. And then it can have a coefficient which is linear in lambda, quadratic in lambda, and the maximum term we can have is cubic term in lambda, because that is what is predicted from a perturbation theory. We cannot have higher terms than that. And all of these coefficients are functions of temperature and the light quark mass. So here we plot, so I am showing our results, which is the work of my student Ravi. So here we plot the eigenvalue density as a function of the eigenvalue at temperatures which is below the chiral symmetry restoration temperature. So this is in the chiral symmetry broken phase. And these are two lattice spacings. This larger number here corresponds to a final lattice size. So it's more closer to the continuum limit. So what one sees is there's a finite intercept here, and then there's a linearly rising part of the eigenvalue spectrum, which we call as the bulk part. And both of this intercept and the bulk actually has predictions from chiral perturbation theory. And we see that indeed all of these predictions work very well. So the intercept is related to the chiral condensate, and if one extracts this chiral condensate, then one can predict the slope of this bulk part. And this slope goes as the fourth power of the chiral condensate divided by the pion decay constant at 0 temperature. So we find excellent agreement with chiral perturbation theory predictions in the chiral symmetry broken phase. Now what happens when we increase the temperature? This is in the phase where the non-singlet part of chiral symmetry is restored. Then what one sees is as one goes to finer and finer lattice spacings, one sees there is a onset of a small pile up of near zero peaks, and then there is this linearly rising part which is called the bulk part. And these peaks become more and more prominent at temperatures as we go from below the transition temperature to higher, and then it disappears at very high temperatures. And one can characterize this slope, and the slope has a finite the slope of this straight line has a part which is independent of the mass, so it should survive also in the chiral limit, and this will lead to U1 breaking. That is one of the interesting results we had. And note that this is still, this behavior here is still not characterized by a lambda cube behavior, which is a necessary condition for U1 breaking that was derived analytically. So we see that the non-singlet part of chiral symmetry is not immediately restored as soon as the singlet part of the chiral symmetry is not immediately restored whenever the chiral symmetry is restored. So this restoration happens at a different temperature. And now one can also study what happens to the lowest part of the eigenvalue spectrum, so these parts. So below TC, of course, we saw that the eigenvalue spectrum has this peak-like structure, whereas at the higher temperature it has a more flatter structure. And one can compare with the chiral random matrix theory prediction. This is given with a red line. Of course, the prediction will not match very well because the random matrix calculations are all done in 0 temperature. We are here at finite temperature, and we know that at 145 MeV, always there is some problem with the chiral perturbation theory about the radius of convergence, and there are issues. But still the agreement is very nice because the peak heights are very well matching. And also one can compare this lowest part of the eigenvalue spectrum. So here we have deflated the lower part of the spectrum by multiplying with a constant which depends on the chiral condensate. So this is essentially zooming in the small eigenvalue sector very well. And what we see is that at very high temperatures, there are no features. So there is a flat like structure, Whereas if one goes to a chiral symmetry broken phase, there is an oscillation here, which matches very well with the random matrix theory predictions. And some people have also tried to get these predictions from random matrix theory from a model, instanton liquid model. So, but I would not like to go into details of it. But yeah. And then, of course, we can calculate this difference between this correlation function, which is an observable which can give us an estimate where the UA1 breaking, it gives an idea about how much the UA1 is broken. And then we see that if we calculate this, these are all done in the continuum limit, so there are no lattice artifacts. All of these are taken into account in the systematic errors. And if we do a 1 by t square fit from chiral perturbation theory, then there is a nice fall off, and we can see that at temperatures which is about 1.2 times this chiral transition temperature, which is around 190 MeV, this part is effectively restored. Of course, always the UA1 breaking will be there, but that should come from other sources, and that are much more tiny than this. This is the most dominant source, and this subsides at around 1.2 Tc. So, if we want to interpret our results, so we see that from the hadronic correlation functions, the axial part of the chiral symmetry, the UA1 part, is restored at 1.5 Tc. And this is the part where the near zero or the small eigenvalues separate out from the bulk parts. And if we visualize quarks as many body states moving in the background of this low energy topological states of gauge fields or the instantons, then one can have a nice interpretation. So, at temperatures below the chiral symmetry restoration temperature, the instantons are strongly interacting and provides a very strong disordered potential. And then this is responsible for the linear in lambda dependence for the quark Dirac spectrum. And there is no much temperature dependence, almost similarly behaving at temperatures below this Tc. Whereas, and then of course, this allows us to use random matrix theory to understand the universality class and make some predictions. And this is happening because the potential is disordered. So, all the information, it is strongly interacting, but is so disordered, all the details of the potentials are lost, and then the gross features of the eigenvalue spectrum can be understood in terms of the random matrix theory. Of course, one can do much more. So, these are the recent works that my student Ravi and Harshit did. So, one can look at these eigenvalues more carefully. So, there is this small peaks, and then there is a arm that comes here, and then it rises linearly. Now, what happens to this arm? So, if one looks at the density profile of these arms, so this is the 10th eigenvalue which belongs to the arm, whereas these are the bulk modes which belong to the most right hand side of the spectrum on the linearly rising part. So, these plots one has removed. So, the difference between these two plots are that the temperature fluctuations have been removed through some procedure called unfolding. And then one can see that all of these intermediate eigenvalues which fall in the arm, they have a percolating structure. So, they are not completely delocalized over the lattice, but they have a percolation like structure, whereas all the bulk modes are actually completely delocalized over the lattice except for small fluctuations which comes due to thermal fluctuation. Yeah. And then of course, one can measure the fractal dimensions because it has a fractal like structure, and this fractal dimensions can be also measured from this is measured from some techniques which are called the box counting techniques which Mandelbrot and all pioneered. One can look at these and also compare with something called the inverse participation ratio P2, which measures how delocalized are the eigenvectors of the Dirac operator. So, all of these agree very well for the bulk part. So, deep in the bulk part where everything is disordered, these all estimates agree, but in this small region of the arm of the eigenvalue spectrum where one sees fractal like structures, this fractal dimensions actually goes close to 2.5, and this can be very well argued from the critical exponents of an O4 model. So, O4 symmetry signifies that UA1 is still broken because the symmetry group can be determined from that. And one can calculate the critical exponents beta and nu in our O4 model, spin model, which is very well known. If one puts those values, then the fractal dimension comes out to be 2.5 around. And what we measure from our studies is also coming close in this region of. This happens just above when the non-singlet part of chiral symmetry is restored. So to summarize, now we are going towards precision calculations. So we are now able to understand the precise details of the chiral symmetry restoration, how different subgroups are getting restored at what temperatures, and what are the signals that come out from the study of the microscopic features of the Dirac operator. And it is evident that the anomalous singlet part of the chiral symmetry gets effectively restored at a higher temperature than the non-singlet part. So when in the literature we talk about chiral symmetry restoration, that is the non-singlet part, and the temperature quoted is that. But of course, the singlet part gets restored at a higher temperature. And of course, all of these processes involve subtle interplay of many-body interactions among quarks and the disordered due to the gauge fields, and this microscopic origin and its understanding is still a work in progress. Thank you very much.
So when you talk about U1A restoration, so I guess what it might mean is that when you, because these are instanton effects, so it's e to the minus 8 pi squared by g squared or something. So when you go to high temperatures, the QCD coupling is becoming smaller. So the anomaly does, like for example, axion masses also don't become very small at high temperatures, which also in. So in that sense, it's a very qualitatively very different from the restoration of the chiral symmetry, where which is like something is getting at the ebb or not. Whereas in so I guess there are two physics. Should I understand it like this? That so U1A is restored because we are going through a more weakly coupled.
No, that the picture that you told, that is true at higher temperatures.
Yeah.
Much higher than 2 Tc.
I see.
2 times the transition temperature. Okay. What we were asking is what happens in this region where the non-singlet part is just restored, non-singlet part of chiral symmetry, and then DO1 is broken or not. That what we want to.
So what I'm
that comes
trying
from
to
this hadron correlation function, and not just from the dilute instant.
So I guess what I'm asking, why do you expect the U1A to be restored? Is it because at high temperatures these instantons won't be, because the QCD coupling is becoming smaller? Like maybe it's very naive way of thinking.
So as you said, that is true. Means it is always broken. We always call it as an effective restoration. So
but if you take G to be very small, it's a very exponentially suppressed.
Yes. So what happens is if you go to higher temperatures, then if one has this kind of dilute instanton gas-like picture, then all of these correlation function that we were studying, they have a very sharp temperature dependence. It drops very sharply. It goes as temperature to the power -8. Whereas what we are studying is when this dominant contribution, which is given by temperature to the -2, that subsides. And of course, that will be taken over at higher temperature by those contributions. So those are the subdominant, which will always be there, but as a background. It will be there till asymptotically high temperature because there will be always some residual instanton fluctuations.
Thank you. Okay.